Hey everybody, in this video we're going to talk about a graphical solution to differential equations. And so far what we've done is we've solved them algebraically, we've applied them in context to exponential growth and decay situations. But today what I want to do in this video is talk about what that graphical solution is, or that graphical context is to differential equations. And so this video is going to cover what's called slope fields. And what is a slope field, you may be wondering? Here's a picture of one. A slope field is basically this. It's a graph that's filled with tiny little tick marks, or specifically slope tick marks, slope markings across the grid at many different ordered pairs across the coordinate plane. It's called a slope field. It's a map that sort of depicts the family of functions that would potentially fit into the solution set of a differential equation. What a slope field does for us is it maps out the different values of the rate of change, the dy dx values, at various places where x changes and where y changes. So at any ordered pair, x comma y, I can figure out what my slope tick mark could be. So that's a slope field. And what we'll do here in this video is try our hand at making our own slope fields. And then we'll actually try to match up a differential equation to one of the specific slope fields. So here's the document for today. This is video 10.3, where we're going to solve differential equations graphically through the use of slope fields. So look with me at number 1. Here's the differential equation. dy dx is defined as simply y minus 1. Now, it says to sketch a slope field at the 9 indicated points on each one of these grids. And the 9 points are basically just shown here by these little dots. So the first ordered pair here on the upper left would be the ordered pair -1, 3. So what I would like to do is plot a little slope tick mark on the dot at -1, 3. But I need to know what kind of slope to sketch. Am I sketching a positive slope, a horizontal slope? Is it a negative slope? And then what is the steepness of the slope? So I really want to get specific and figure out what the value is of my derivative. So dy dx at the point -1, 3, plug in -1, 3 into dy dx. There is no x in this case, I'm just going to plug in a 3. 3 minus 1 is 2. So I have a slope of 2 on that first little point. I'm going to draw a tick mark of a slanted line that looks like it has a slope of positive 2. 0, 3, same thing. It's going to have a slope of 2. And 1, 3, again, there's no x in this dy dx expression, so it's only going to be dependent on that y coordinate. So another slope of 2 across the way over there. And then on the left, I'm just sort of showing you what we're doing here. dy dx evaluated at the point -1, 3, and then 0, 3. Here's one where I evaluated the derivative at -1, 2. That slope would be positive 1, so a little bit less right there. Less steep of a slope that I had earlier. And then, of course, 0, 2 would have a slope of 1. 1, 1, another slope of 1. But then what's going on at these lower points? -1, positive 1, 0, 1, and then 1, 1. Well, when y equals 1, dy dx, the slope, is equal to 0. So I have a horizontal on all 3 of those points. And that would be my slope field sketch. You don't necessarily have to write out the computations. I'm just sort of showing you where and how we come up with those different slope values, the tick mark slants and steepnesses. Number 2 is over here. Let's try this one. So again, quite a bit more complicated because I have x's and y's and they're being squared. There's a 1/2 multiplier, so we've got to be a little bit more careful about how I map out these slopes. So plug in -1 for x, plug in 3 for y. And let's take a look at this next slope field. I'll have 1/2 times 1 plus 9, which is simply 5. So a pretty steep slope at the ordered pair -1, 3. And it should be, we're not going to really be looking at, is it a perfect slope of 5, or does your line look more like a slope of 3, and so that you would maybe lose accuracy points or something like that. That is not the case. Essentially, we're just looking to map out these slope tick marks. The horizontals should be pretty accurate whenever your derivative values are 0, and then positive slants versus negative slants should also be noted. 0, 3, I have a slope of 4.5, and then 1, 1, I'm back up actually to a slope of positive 5, so pretty steep slope right there. I'll fill out the rest for you here. You can check those on your own. So some slopes kind of like that are how I would finish off that slope field. Go ahead and pause the video at this point, and why don't you try 3 and 4 on your own. The slope fields are y divided by x, and number 4, x minus y. So what would be the values of those derivatives as you plug in your x, y coordinates? And as I'm filling this in for you, notice that you might have an undefined slope, in which case we'd have a vertical line or a vertical tick mark. And so there's a horizontal at 1, 1. And there you have it. So those are 4 examples of how we can construct our own slope fields on a series of, in this case, 9 little grid points. Now, let's take that a step further. This second part of the video is going to involve us matching a differential equation to its actual slope field. So, a couple things to keep in mind. Before we go to the matching portion here, notice this at the top of the paper. Remember that solutions to differential equations have to be functions. They must be continuous and differentiable functions, more specifically. And finally, they have to have a domain that contains the initial condition. So more on that to come, because what we're going to do in addition to matching the differential equations to the slope fields is we're also going to sketch a function curve that will be the particular solution on top of the slope field. But first, let's try to match. So I put some notes down here for each one of these. Notice that in the first one, number 5, dy dx is equal to simply x. Well, if that's true, then the columns along the slope field will all remain consistent, okay, because that dy dx value does not depend on y. So all of the columns will be the same. Let's see if I can find where that happens in these 6 pictures down below. If you look at picture C with me right here, look at how all of the columns have the exact same slope field tick marks. When x equals 0, the slopes are all 0. When x equals 1, the slopes are all 1. When x equals -2, the slopes are all -2 up and down those columns. So choice C would be the correct match right there for number 5. And look down at number 8 for a minute. 8 says dy dx is equal to y. So now it's going to be those rows that are consistent across the board in that slope field. And which picture here has consistent rows? How about picture F? So when y equals 1, the slope is 1 all across that y value there. When y equals 2, for all the different y equals 2s, the slopes are 2. And when y is negative, -5, -3, all the slopes are going to be the same across the row, because that one does not depend on x. So choice F would fit nicely in that choice. Then for 6, it has dy dx equal to x minus y, and then problem 9 right below it, dy dx is equal to y minus x. So the note that I left myself here is just that we're looking for slopes that are pretty steep, increasing when x is greater than y. For problem number 9, the slopes would be increasing when y is greater than x. So where does that happen? Can you figure out from the slope fields which ones match up with those? Take a look at choice A to match up with 6. Take a look at choice E to match up with problem 9. And then finally, let's look at 7 and 10. So these are quotients. And with quotients, I try to find where I have horizontal slopes whenever the numerator is equal to 0, or where do I have undefined slopes, vertical slopes, when the denominator equals 0. So if I have y over x, negative y over x in this case, then I'm searching for horizontal tick marks on the slope field whenever y is equal to 0, and vertical tick marks whenever x is equal to 0. So are there any horizontals when y equals 0? And are there any verticals when x equals 0? That looks like right here in slope field letter B. Here are the verticals right there when x equals 0. And I've got horizontals right here when y equals 0. And the flip of that would be my remaining slope field here, choice D. I have horizontals when x equals 0, and I have verticals when y equals 0. So those are just some little clues and tips to help you match differential equations to their slope fields. Now, the second part of this activity says to sketch the graph of the particular solution through the highlighted point, or the point there that's shown, 3, 2. And so what I'm going to do now is go through each one of these pictures, and I'm going to sketch what's called the particular solution through the point. Now remember, again, back to these comments I highlighted, what I sketch here must be continuous, it must be a function, and it must contain the initial condition. And when you draw your solution here, it's got to go through the point, and think about kind of dropping a twig in a river, and that river has currents, and so the little twig that you drop is at the mercy of the current, and it's going to flow or sort of travel wherever the current takes it. So likewise, if you're dropping a little stick or twig in this current of slopes, it has to sort of follow the slopes. Look at letter B. Here's my ordered pair, 3, 2. I'm going to be drawing my solution sketch that always runs parallel with those slopes, along with the slopes. You never want to go against them. You never want to be crossing through any of those slopes. So kind of make sure you're always moving parallel as you sketch those function curves. Letter C, I'm going to go through my initial condition. I'm going to follow those slopes. So maybe something like that would be my sketch for letter C. Looks like a parabola. Letter D. Be careful with letter D. This sort of looks circular in nature, but do not draw a circle, because a circle or an ellipse is not a function. So I actually want to just sort of end my sketch for letter D right there. Put a little note to yourself on slope field letter D that your sketch must be a function. So I don't want to draw a full ellipse, a full circle. That's not a function. In this case, it's that upper half. It's sort of like the upper root that we'd use. And then finally, letters E and F. I try to start from my initial condition. Maybe something like that. And then letter F over here. This almost looks exponential. And there we have it. So those are 6 different particular solutions through the given initial condition that sort of fit on top of the slope field sketches. Now, one last thing. If you would like to check that you maybe matched up your differential equations to the correct slope field, there is a really nice slope field generator on DESMOS. And all you would need to do is simply go to Google and type in slope field generator. And the first entry that pops up is the DESMOS Slope Field Generator. So feel free to just click that and open it up. And what you should see is just a place for you to type in any dy dx equation that you want. Here's the default one, but let's change it. The very first one that we wanted to sketch was y minus 1. There's what it looks like. So I could zoom in to that section of the grid between -1 and 1, up from 0 up to 3, and I could see if my slopes actually match what I sketched. Or maybe I'm trying to match up this activity that we just completed. So what if we wanted to check something like negative x over y? Negative x over y. This is problem number 10 from the slope field match, and there it is. So I can see that what I matched up on my paper actually is confirmed by the DESMOS Slope Field Generator. And there's even this little grid point that you can move around the slope field, and as you move that grid point, you can see how it's always going to be parallel with all the slopes that you see, and it's never going to be kind of slicing through, cutting through, or intersecting any of those slopes, but rather just running parallel with them and kind of staying together with that again, that image of a current in the river. So slope fields kind of give you that graphical solution of what differential equations do. And I hope that after this video, you have a good sense of what they mean and how they work.